Hello, everyone. My name is Cynthia Blankenship. I'm the president of the Geologists of Jackson Hole and a member of the Speakers Committee. And due to some technical difficulties the other night, I'm having to re-record the introduction to Dr. Ryan Thigpen, my very good friend. Ryan got his Bachelor of Science in Geological Sciences at the University of Tennessee in Knoxville in 2003. His master's in Earth and Planetary Sciences, also at the University of Tennessee in 2005. And he got his PhD in Geosciences at Virginia Tech in 2009, which is where he started dating his wife, Summer Brown, who is also a geologist. Ryan was then visiting assistant professor at the College of William and Mary from 2009 to 2010. In 2010, Ryan joined BP America, which is where we met. Ryan was in our structural geology and geomechanics group from 2010 to 2015. In 2015, despite my urging him not to, Ryan left BP to return to academia as a professor at the University of Kentucky, where he is now. He is currently working on projects in the Himalayas, the Appalachians, Scotland, and of course the Tetons. Ryan's work started in the Tetons in 2008. When he set out to impress his girlfriend, Summer Brown, by fetching rocks from the Teton peaks for her to study. This led him to start his own projects here, and tonight he is going to share with us the results of his team's work coring Jackson Lake last summer. His talk is Hunting Teton Paleo-Earthquake Records in the Deep Parts of Jackson Lake. Now over to Ryan.
Thanks, everyone, and thank you to Cynthia and Dan for hosting me again. They have put together my favorite bed and breakfast in the greater Teton range. So it's my favorite place to hide out from the world. And this is April and October, actually my favorite months to be here. I'm not a big fan of all the crowds. I'm interested to see with some of the challenges that I know the Park Service has been facing. We're interested to see what the buffalo petting season is going to be like this year. So, this has always been one of my favorite places in the world. And I've been really fortunate to get to work here. I'm excited that Simeon gets to join us today. Just saw him back there in the back. He was kind of instrumental, along with other folks at the Park Service, in helping us pull this off. When you're a former oil company employee that goes to the National Park Service and asks to poke a drill hole in one of the most beautiful lakes in the country, it's a little bit unnerving for everybody, including me. It took a while to get permission to do this, but I'm hoping what I can show you today is that what we found is sort of, it was worth the effort. It was sort of singular and incredibly cool. NSF has supported all of this work along with some startup grants we got from the.
Sorry, Mark, there's not any sound on Zoom. We need to change the microphone to the wireless GoPro.
Is it this one? Does this one work?
It works, but you got to change the input to that. I think.
On where? Let's see.
We can hear you now.
Okay, everyone can hear okay? Okay, everybody good? Okay.
Sounds good.
All right. So this operation was part of a bigger project that NSF funded. The National Park Service research station run by the University of Wyoming housed us a number of years. In fact, some of the crazy ideas that I've had about this place have come on rain days there. When we've exhausted the boxed wine supply at the Coulter Bay General Store, and everybody that spent time up there knows what I mean. But we've put this together over a number of years, and so there's a lot of people that are involved, and that's why it says University of Kentucky team instead of my name, because I can't take credit for this. Because there's a ton of people that have been a part of this work that have joined us in doing this. So Mike McGlew and Ed Woolery are my seismic and lake collaborators. A lot of the coring stuff you're going to see today is largely driven by Mike McGlew. He's an incredible lake coring guy, does this stuff all over the world. Summer Brown, my wife, who started this project in 2008 and has stayed attached to it. She's also a professional photographer, and so a lot of the incredible photos you'll see in this talk are from her, including that first photo that I should have mentioned was the National Science Foundation's Mr. or Mrs. February in the calendar this year, depending on your vibe there. My dad joined us out there to help cook. I've had a ton of students. There's our coring team with the great team from Minnesota. And actually, I've now decided it's time for this project to end because I can't add anybody else because we've run out of space on the screen. So this slide is at maximum density, but I do this because this has actually been the most rewarding part of this work. Every single one of these students you see here has played a major role. Every one of the students in that picture from my 2021 research group, which is way too big, all played a role. 2022, and so getting to do this with so many students and so many other people has really been incredible. So I always have this start out slide for all my talks. I hope you guys all know where you are, but we're here, of course, in the Teton Range. And this is the Yellowstone hotspot tracking across here. And a lot of the work that my team has done has been focused on the tectonics of the region, specifically the long-term tectonics, the uplift of the Teton Range, the potential extensions of the Teton Fault, which we hypothesized just to get people upset here, get their blood moving. It's a pretty simple range, though. When you think about it in its most basic sense, it's just one big normal fault, right? That cuts through the range. It's an active normal fault, a beautiful active normal fault that creates the footwall range uplifted. That's the Tetons, and of course the Jackson Hole Valley is the hanging wall of this big fault. But things get really complicated when we get into the more recent history of the Tetons, a little bit more enigmatic because we don't have a great handle on the earthquake evolution of this system. So if you look in the incredible LiDAR data that the Park Service collected in 2014, as my old advisor used to say, if you can't see the fault in this picture, you should find something else to do. And it is really a spectacular image cutting through these glacial moraines, mostly of Pinedale age, about 14,000 years old. I'm always amazed you can see the recessions in these things. It's really incredible data. But we have this beautiful scarp cutting through here, and it's anywhere from 12 to say 27 meters, depending on the age of the scarp that it cuts. But what's really interesting about that is that in most cases, when we cut a trench, I haven't actually done this, but when a lot of these incredible studies I'm about to talk about will cut a trench across this, they can only find 2 and sometimes 3 slip events that total usually around 4 to 5 meters of slip. And the scarp in most places has like 12 meters. So we're missing a lot of even the most recent earthquake history in this system. And so I'm going to go from north to south here and talk about some of those studies. Sorry, it's too dry out here. I got to go back to where it's flooding. We start in the south there at Teton Village at Buffalo Bowl. This is in Cynthia and Dan's backyard, this trench. This was a USGS trench. It was actually dug with heavy machinery. It's one of the only places we can do this because it's not national park. I haven't talked to Simeon about bringing an excavator into the park yet, but I suspect that's going to be even more challenging than the coring rig. But we've got Chris DeRoss there in the trench for scale. And this was the biggest trench at Buffalo Bowl. They identified 3 slip events that they were able to date at 4.6, about 7.1, and about 9.9 thousand years ago. Moving north to Granite Canyon, John Bird did a study across the fault right there, where he was able to find a 6.3 and an 8.1 event. At Jenny Lake, this is Darren Larson really kicked all this lake stuff off by doing this coring work in Jenny Lake, where he thinks he has identified 8 earthquakes. This was published in 2019. These are based on these big sandy, I got to remember to use my arrow and not the pointer, these big sandy turbidite bodies that we get that grade from coarse grain stuff to the finer grain stuff. And this is kind of like where a landslide goes into the lake, or where you have an underwater landslide caused by the shaking. And that's something that's going to be a recurring theme here. Moving north to Lee Lake, there's a bunch of imbricated scarps that are right here on the shore of Lee Lake. And they picked up the 10 and the 5.9 earthquakes there. And then in the far north at Steamboat Mountain, they picked up 2 quakes, the 5.5 and the 9.7. And this is this trench was dug across those scarps that cross Jackson Lake in the very far northern parts, where we a lot of people suspect, not we, I won't say we, but a lot of people suspect the Teton fault is dying up there, but it's interesting because there's still some pretty big slip events up there. That scarp in the middle of it is about 12 meters tall, just like the ones in the south. And so this is what we put together, all these earthquakes. We sort of come up with basically 3 big events at 5, 8, and 10. Okay, and then there's a bunch of these subsidiary events that Darren may have discovered in this really more sensitive record in Jenny Lake. So there's a difference here in these records. So it's not always the most direct comparison. And I think it's important to talk about this. Trench records are challenging. We're going to dig a trench across a fault, and we're going to try to find sediments that show thickening and thinning patterns that tell us when the fault has moved. So we're trying to directly date the fault. The challenge is we're having to employ a bunch of different kinds of geochronology that's also got its own challenges. And we really need to, these slip events need to be preserved. Things can't get eroded before they get buried. So these terrestrial trenches can be really, they're direct records of the fault, but they can be challenging to both date and interpret. When we go to lake studies, we're really looking for things like underwater landslides or some other evidence of seismic. These are generally much better preserved. They're generally much higher fidelity. But the challenge is we're having to make this leap from something that's not a direct slip on the fault. It's a consequence of the shaking that resulted from the earthquakes. And so the record's a little bit less direct. And so there's trade-offs for both. And so we're always trying to put these pieces together. And this is kind of the essence of paleoseismology, I think, makes it one of the most perfect geological sciences, because there's a lot of technical rigor that goes into it, but there's a lot of art to being able to put all these interpretations together and make this work. And all these guys up here are really great at doing this. I'm definitely an amateur paleoseismologist, and so I aspire to catch up with these guys one day. So this is what that record looks like if you plot all those samples up on just a simple diagram going from youngest on the left to oldest on the right. And what you'll notice is there's a lot of dark blue over here on this side, right? We're missing any earthquake events in the last 5,000 years. And this is a big problem, because if this fault's slipping every 1,000 or 2,000 years, and then 5,000 years ago, it just stops, there's sort of 2 possibilities there, right? One is that the Teton fault is done. We happen to, to have just come in and bought real estate at the time when the Teton fault decided to quit moving, right? Raise your hand if you believe this to be true. Yeah, there we go. All right, we have a couple. That's fair enough. It seems to be the ones that live closest to the fault, I noticed, that were clapping. So the other possibility here is that the Teton fault is storing up for a really big earthquake, right? That's what faults do. Faults accumulate strain until something causes the fault to slip, and then it releases all that strain through this energy release, and we get an earthquake. The Saigon fault that happened in Myanmar last week was a perfect example of what happens when we have a big seismic gap in a fault, a section of the fault that hasn't moved in a long time that should have, and finally it goes, and the next thing you know, you're in a swimming pool on top of a hotel in a Bangkok, and you're swimming in the waves, right? It's just really scary if you haven't seen these videos. So this is important to get this right. Now, there's a third possibility here, and that's that we just haven't seen it in the record. That happens all the time in paleoseismology because, as I said, these records are challenging and often incomplete. So maybe there's something we're missing. So my team has largely before this been focused on things like the geometry of the fault and the uplift of the fault. I've had a bunch of students working out here on different parts of the larger tectonics. They've been doing things like mapping in the new LiDAR and trying to link fault systems together and try to understand the geometry of all these things. And we draw these elaborate 3D diagrams to try to explain all the things that we're seeing. But at the end of the day, the most fundamental thing that we need to do in the Tetons is to get the earthquake record right. And that's what all of these guys from the USGS and from other universities have been doing all these years. And so today what I'm going to do is show you our contribution to that effort that kind of happened, to be honest, as a little bit of an accident. So we came out here, my colleague there at the top with the hat on, that's Mike McGlew. This was his field assistant at the time, Joseph. And Joseph drove the boat in an incredibly straight line. I never met anybody that could drive a boat with a tiller this straight. He was key to making all of these lines straight. But those guys would actually go out and shoot seismic. This is our grid. It's an incredible 2D seismic grid. If any of you have ever shot seismic before, you know the epic amount of time and effort that goes into something like this. So this was a few years of shooting seismic. The other thing we know about doing seismic is that sometimes you get lucky and sometimes you don't. And in the Tetons, we got lucky. This was the kind of data, as my colleague Ed Woolery said, this is the kind of data that I would want to sell this instrument. This was a 500-pound towfish. We called it the yellow submarine. I hated this thing. There were no handles that were really easy to grab. It was really heavy, but it took these incredible images. This is basically just an $80,000 fish finder. This is up at Arizona Creek Delta. So right where Arizona Creek comes in north of Coulter Bay, and you can see these incredible folds. You can see all this sediment structure filling in, all this incredible down dip deformation that's being onlapped by these unconformities, these prograding delta fronts, all this stuff that you would use. You use this stuff to teach sequence stratigraphy in a class at university. This is really incredible data. This is down further south. I should have mentioned that the map showing where these seismic lines come from is over here. This one goes across Moraine Bay. You can see Moraine Bay perched up here, this beautiful perched basin. We've drawn some of the sediment packages in here. It's really incredible. We actually have John Dilworth, one of our students, published data from another coring operation that we did in Moraine Bay. And then, of course, the main Jackson Lake Depot Center. And the data is just really spectacular. But when we got into this data, so this is in the main Teton Depot Center. And as anybody that's worked in industry or worked with seismic data knows, geophysicists like to take data and vertically exaggerate it to the point that nothing's real anymore. So this is like a 12-to-1 vertical exaggeration. So you have on the west side, sort of the probably a proto-fault scarp, like part of the Teton front. And then you've got this big basin here full of sediment. And then you've got this stuff over here. And this acoustic, what we call acoustic basement, it's basically the place where we don't get any more energy returns. This is actually, we think this is all glacial till. So what we're looking at is the till. And then you've got this beautiful sediment package on top of it. And of course, this is all water. The surface of the water be up here somewhere. But in the deep part of Jackson Lake, what we started seeing immediately were these big lozenges of no or really low reflectivity material. These are giant underwater landslides. We call them mass transport deposits or mass transport complexes that slide down off these steep flanks. Well, they're actually not this steep when you turn it down the vertical exaggeration. I'll show you that in a minute. It's not as steep, but they still slide down. And we think that these are largely driven by seismic processes. These things, and there's a ton of them. When you really start to hone your eyes in, whenever you have regular sedimentation in this lake, this is what we would call the railroad tracks, or like the slow lake sedimentation. It lays down these perfectly parallel layers, and then all of a sudden you'll just get one of these big slumps of material that will come in, and you can see them on the edges here in a bunch of places. So we started thinking about doing earthquake studies using some of these. And the first place that I was kind of inspired to do this, I was actually driving through the Dunche Valley in Nepal right after the Gorkha earthquake. And so you can see this really scary road that this is like a dirt road they've just chopped out of the side of the cliff. I was just there a few weeks ago. The road is scarier than it was the first time. So I don't know if I'm getting older, the road's getting sketchier. But I'm going to look across the valley and you can actually see all of these gray streaks. Every single little ditch of a thing had a landslide deposit in it. Almost all these landslides came down during this huge earthquake. So it started getting us thinking about the whole, in geology, we've always had this idea that everything happens really, really slow. But it's probably not the case. I worked a lot of the stuff with my wife. We worked a lot of the stuff during Helene, and it was incredible to see the amount of erosion, both landslide and fluvial river erosion, that happened during that event. And so we started thinking about how many landslides we would expect to see in these basins during this time. And it turns out some lakes folks have already done this. And I'm embarrassed to say that in my scramble today, so my sump pump went out. I was in the Kentucky floods this weekend, and my sump pump went out right before I had to come here. And I've never dealt with a sump pump before, but now I know how to fix one if anybody needs any help. But I got behind on things, and I don't have the reference for this. But there's an idea in lake studies called the synchronicity criterion, where a lot of mass transport deposits will show up at the same time. And when that happens, the chances they're non-seismically driven is pretty small, right? So what we have to do is get into this data and find these slump deposits, and then find the intervals where there's a bunch of them happening at once, right? That's the first part of this. So this is that data I promised you. This is actually only a vertically exaggerated 4-to-1, and you can see it doesn't look quite as wild. But in here, we can actually get in and map all these features out. So we started doing all this mapping, and I'm going to show you some more of this seismic data, but we basically found a number of these big deposits where there were a whole bunch of them lumped together. We started calling them groups, and this work was done by my master's student, Callie Cortese, a couple of years ago. Callie did an incredible job, mapped the whole basin, all the horizons, and then went through looking for these slump deposits. Some of them are smaller. Some of them are actually quite large. I'll tell you a little story about this gigantic monster right here. But we picked, after we got done mapping, we said, okay, we know where these slumps are, where these instantaneous slumps are. And I'm going to show you some maps of these things. But now we need to know how old they are. Now we need to figure out when these what we think are earthquake events actually happened. So we came into core this thing, and we wanted to intercept as many of these horizons as we could. But as Cynthia mentioned, I worked for BP, and I started in 2010. And I don't know if anybody remembers what was going on at BP in 2010, but a lot would be the answer with the Deepwater Horizon incident. And when I saw this big underwater slide, our data was so good, you can actually see these little, I'm going to show a close-up of this in a minute, but these little vertical things coming out of it, the like degassing and dewatering features from where this thing slides down and doesn't have time to squeeze all the water out. And I was imagining us poking a hole in this and turning Jackson Lake into this brown, ugly thing. And I had some 2010 flashbacks, and I was like, yeah, we're going to go just to the left. We're going to avoid that guy altogether. So that's where we sighted our core that we ended up taking. And so this is a little video, a quick video about how we took this core, just to show you. But because the video goes quickly, I want to explain a little bit about what you're going to see. So the coring rig shows up from the University of Minnesota, and it comes in a container ship. It's Austrian built. It's built to break down into small enough pieces they can fly it anywhere. They actually flew this thing to Guatemala right after they left the Tetons and built it and tore it down 13 times, which when you see this thing in operation, you'll be like, wow, that's ridiculous. Because it was Austrian built, every single bolt was different, right? So you had to find the right bolt. We dropped some in the water at Leaks Marina, and it's like 10 feet down of cold water, and you could see the bolt on the bottom, and you knew there wasn't a replacement in town. So then we had to, do paper, rock, scissors and see who was going swimming. We built it on the shores in October. Simeon did not want this circus there in September or August. We drove it out onto the lake. We went to the deepest part of the lake because that's where the sediment package is the thickest. We put a big weight on the bottom that had some cables that went up to the rig. There's a big, it looks like a giant oil funnel, the reentry cone that goes down to the bottom. And then we slide this assembly down to the lake floor. And then we use an 80-kilogram weight to hammer these rods into the lake floor. And the rod at the front has a piston on it. And when we get ready to start coring, when we're at the depth we want to start coring, we pull a cable, and that piston slides up the barrel, and it goes 1.5 meters into this sediment. And then we pull it all the way back up. There's a thing at the bottom called the core catcher. Core catcher locks it off. We pull it back to the surface. Then we take it to the University of Minnesota and process it. So I'm just going to let you see this quick video that shows. Oh, sorry. Oh, let's go back. Come on now. Sorry. I don't know if they can, there's music with it and it doesn't really matter, but I don't know how to make that little sound. That's the rig when it's fully assembled. Took us, I think, 2 days to put it all together. And these guys, these these guys from the University of Minnesota, where this is what they do. They just travel around the world doing this. So they're incredible. And my colleague Dan and my wife Summer shot all this video. So that was also an incredible feat with a bunch of weirdos and a cabin. That was the smoothest day I'd ever seen on Jackson Lake, the day we set the coring rig in place. It was incredible. We had to put anchors out in 400 feet of water that had to be 900,000 feet from the boat. So it was the first time I ever had to use Google. There's the every inch of the boat. We had to use Google to figure out where those anchors would go. It slides down the cables to the bottom. That's the hammer rig. Go back up. It's a nice, long, gray mudstone. They looked very uninteresting if they were plastic liners, but they would turn out to be. We named the core the J-hole. I was a college dropout, dirtbag skier. That was the called place. And we would come skiing here, so we had to come up with a 5-character name. Like, well, that's I'm still trying to figure out what to do. Mike's the expert in handling the We had to put river buckle straps on because there was no gas. Then they go to Minnesota to this facility made just to process lakeport. Just put them open, special saw. Come open. Image that we had only like we had about 10 minutes, 15 minutes max. Get them on the imager before they oxygen. Water. Like I said, with radiocarbon. So I guess you could go get them and bring them here to you. So, yeah. We were able to collect about 31 meters of core, about 100 feet. Sorry, let me go back to this. We got down to just below the Holocene-Pleistocene boundary. So this was the full core. Each one of those little intervals, the ticks you see on there, those are the core barrels. And so we start at the bottom. Apparently, I'm learning all this lake stuff from my colleagues, but you always start at the bottom and work your way up. We split the first core, and we were immediately excited because we thought the bottom of this hole would be the Pleistocene. This would be the glacial stuff. We split the first core, and we were into the glacial varve. So these varves, this is what it looks like when you have a glacial lake. You get these really pronounced, they look like tree rings. You can count them as years through the summer and the winter of each year. And these are really spectacular. And we got even more lucky. This little white band right here, that's the tephra from the Glacier Peak eruption coming from Washington about 11.2 thousand years ago. So right here at the bottom, we got really lucky. So I'm going to show you what some of these events look like in this core. So the first event that we actually found in this system, we weren't able to get down to. This is where we were trying to go. But based on the geochronology that we're able to do on these cores, we think that this P11 event down here in the Pleistocene is probably 13 to 14,000. I do want to emphasize that that I'm going to have to go back to the Park Service and ask them for another permit to go another 60 meters down. This record that's down here might be like a singular record in North America, because we don't have a lot of lake holes like this that have this sort of information. And it's not just earthquakes. There's climate and lake evolution and ecology and all these other things that are stored in here. And so we've only done a third of this record so far. Moving up, we start seeing a bunch of these little turbidites, and they're little sandy guys that they got real coarse sand. You can see the varve ends, you get this really sandy bit, and then you have these clay caps, and we think this clay cap is like the final settling of these things. This one's only about 4 centimeters. These are pretty small, but we see a lot of these, and it's hard to get a turbidite this small into deep water. So these are ones we're sort of thinking about. This one's about 12,000 years old. I should have mentioned that when we did this, we had 45 radiocarbon ages through the core, and then we had the tephra at the bottom, and we build what's called an age model. So all of these ages that you'll see, these are based on the age model that we built. We use a statistical program to do this, where we input all the data and all the errors and try to find the closest thing we can to date each one of these horizons based on the depth and the sediment accumulation in the core. Moving up section, we start to see our first MTD. I'm embarrassed to say this right here is where we opened it up, and we would normally clean these cores before we would image them. We started cleaning this one before we realized this was an incredible injectite, where one of these MTDs had come down and kind of injected itself into the soft sediment. And so I'm going to take responsibility for this upper section. But this was our first MTD event about 11.8 thousand years ago. MTD, a mass transport. This is the mass transport deposits I talked about at the beginning.
What's the age of the deepest core?
It's right around 11.5-ish.
11,500.
Yeah, I don't know. It's probably it might be like 11.8, 11.9, something like that. It's hard. We have a little bit of disagreement between our tephra layer and our radiocarbon, but it's only a few hundred years. But it's probably right around 12, 11.5 to 12. These are a couple turbidites that we get up section. We actually have a lot of these. I'm not going to show many more of these, but they're these beautiful turbidites, once again, sandy with these white clay caps. But what's incredible about these is we think some of these things might be aftershocks or foreshocks for some of these big events, because we'll get them and then we can count the varve cycles, and we're usually on the order of a few tens of years out from some of these earthquakes. Moving up section, we get into some of the really big, the bigger deposits. So up here, we've got, you can actually see, if you look closely, you can actually see there's layers in this, and they're folded. So this is where these deposits come down slope and they sort of roll over, or they thrust fault, or they do, all the deforming things they do. That's right here at the top of the barrel. And then if you go to the next core, you'll actually see there's that clay cap, and it's getting thicker. The bigger these deposits were, the thicker the clay cap. We've speculated that these clay caps might be the seiche. So the seiche is when you have an earthquake that shakes a lake, and it's just shaking back and forth, and it takes a while to shake all that sediment out. It disturbs all the finest grained sediment, and it takes a while to shake it out. Now, another way you can do this, obviously, is with a catastrophic flood, and this is what we saw in Asheville after Helene. The reason they had no water for 3 months is that giant, super fine grained debris flows hit their water reservoir for the city of Asheville. They couldn't get the sediment out. So this is an MTD map of that of this deposit, and you can actually see, so the hotter colors are thicker, the cooler colors are thinner, but you can see there's actually multiple deposits that are associated with this, and we mapped all these out in detail. And so any place that we had at least 5 of these individual deposits mapped out that we could tie to the core, we would say, okay, that's one of our seismic events. So this one's one of the first clear ones, 11,640 years ago. So they started getting more interesting as we moved up the core. And what was this? Some of these big thick ones were really unique because we couldn't see them in the seismic data, but they would show up. We'd get these incredible, really deformed sections in the core barrels. You can see the glacial varve down there. And then all of a sudden, we've got this big thick section of deformation. So this one was at 11,500 years. Moving up section again, we get into some of the even bigger ones. You can see this really coarse grained stuff at the bottom. It's finding up through these sand packages to the top. There's our beautiful clay cap, and then we go right back to lake sedimentation. And note, in this one, we've gone out of the glacial varve. So we've left the glacial interval for the Tetons at this depth here. This big debris, I'm sorry, I'm using this thing like I'm not supposed to. This big MTD that we see in the core is this orange unit that you see here, this really good looking unit. And if you're at AGU in Washington, D.C., LACOR actually made a bookmark out of these, and I meant to bring some of these to give away. But I'll try to send Cynthia some to give away at one of these meetings. But this is now the finest bookmark in their collection. This is what the MTD map of this one looked like. It was an incredible earthquake. This is that 10,000-year earthquake that we see in all the other records. I'm doing it again. The 10,000-year earthquake. And you can see all these red. These are all individual MTD events that shook into the deep depot center from that earthquake event. So there's our 10,000-year earthquake. We keep moving up section. We get into some smaller debris flows. This one is coming up on this convergence of a bunch of stuff going on. That's this little star right here. And then we move into the big ones. And you can see actually, there's actually stratigraphic layering and stuff in this barrel, but all this stuff has been deformed as it slid down the slope. So we're into these pink and orange and red units. We actually didn't core this one on purpose, but we're into these guys. And these are all basically inseparable events that are right around 8,000. So we think the 8,000-year event that we've seen in all the other studies that's so incredible in this study is probably the big earthquake in the last 10,000 years. We think this thing was a monster. And so we have a couple of these big debris flows. This is the second one coming up here. And of course, we have this third one over here that I'm going to show you up close. We don't have core of this. But these things were like a couple of core barrels thick. So we got 3-4 meters of sediment deposited here in a total package of 30 meters. That's all from these events, and multiple slides coming down. And we can see in the data, we can actually see in the data where they cross over. But you can see here's, once again, what the map of these MTD events look like. They're coming from all sides of the basin. We even had one over here in this relatively shallow area. This really big, thick guy. And so we've got a lot of activity at 8,000. We think this big giant guy here, and I actually took all the colors off so you could see that I wasn't making this up. Geophysicists that I've worked with have a habit of drawing what they want you to see. So we took this off so you could see both the detail in this and the geometry, but you can actually still see some of these reflectors underneath it. But this thing was so thick and had so much water, you can see where it eats all the energy. We can see nothing underneath it. And there may be another big one right here that we can't even see. We think this represents the collapse of the Snake River Delta during this 8,000-year-old earthquake. So it's a huge earthquake. The whole northern delta of the Snake River collapses into the basin. And once again, you can see all those. These are real features. This is not noise. These are like dewatering or degassing features where this thing is sort of depressurizing. If you zoom into where these all intersect, you can actually work out the relative age of them. And what's incredible is you get this guy down here at the bottom. He's this one here. And then this guy comes in next, the big thick one. And what's incredible, this red, this is a normal fault that formed in the lake during this earthquake event. And this big gravity flow here filled in the accommodation space it produced. So we think that during this event, this normal fault forms, this big slide gets triggered, and it comes in and fills in the space that was made by that event. And then this one comes in over the top of it, onlaps right on it. And we think that because these all have the same top. They all have the same next lake layer coming in over the top. So we think all three of these events happened sequentially, maybe as foreshock and aftershock events. We can't separate them during that 8,000-year event. This is what that big monster slide looks like in the thing. So you can see this is why we think it came from the Snake. Here's the Snake. This is all Snake River Delta sediment that fills the northern part of Jackson Lake. And you can sort of tell by the geometry how this thing slides down the hill, piles up at the bottom, that it came from the delta there. And you can really see the detail in this structure where these onlap. It was really spectacular. Moving up section, we have a few smaller events. This one at about 5,000 years. This is the only record we have of the 5,000-year quake, which was interesting. And some of the other trenches haven't found it too. So that quake to all of us, I think, remains a little bit enigmatic. Moving up section again, though, we find another major MTD event. This one has a nice sandy package, a beautiful potential seiche clay cap on top of it. And this is a really high confidence seismic event. This one's at 3.44. So this is 3,440 years ago. And we think this was, when we found this one, we think this was the youngest quake that we had seen in this record by far. And it's statistically distinguishable from many of the 5,000-year events. Moving up section a little bit further, we actually find another event. And this one's a little trickier because it's not as thick. It's only about 6 centimeters. It's a beautiful turbidite. It does have this interesting carbon layer in it that we're still working on. We don't really understand exactly what's going on here. That event, though, about 2,100 years ago, actually shows up in a bunch of locations. And I've put it here on top of the Group 3 map because we couldn't actually make an isopac map of this guy because the layers were so thin, the layer thickening package we were looking at in this event were so thin that our software struggled to make isopac maps, to make these thickness maps of it. But we do see this event on multiple sides of the basin. So it's not a single landslide event. So we're calling this sort of a medium to high confidence seismic event. It's still something that we're working on, but it's not as clear as the one at say, 3,400 years ago. And then moving up section, we actually get a couple more smaller turbidites, these clay capped events in the section. And so we can take all these events. So that's all the core data. We can take all these events, we can stick them on our graph that we showed at the beginning. And this is what we saw. So this is the turbidites and the MTDs, and I don't have them separated here, largely because we don't really understand how they should be separated at this point. But the J-hole events are all lining up mostly with events we've seen before. We do have a nice 12,000-year event that lines up with what Darren Larson found in Jenny Lake. We think that was also a significant event because we had a lot of turbidites in that section. And so you can see them all there. So we had nothing in the 10,000-year event, which was kind of interesting, but it also begged the question about some of the errors on the ages we get from the trenches. And when I say error, I guess I should actually say uncertainty. This is not one of those things where somebody did something wrong or anything was wrong with it. It's just the inherent challenges with dating some of these things. And so it's possible that we don't have the 10,000-year event up there. It's more likely that either we missed it or that, our ages don't align perfectly with whatever event they had. Because we're in the middle of two places that both saw it, it's unlikely that it didn't occur here. We do have the 8,000-year event. Ours are mostly clustered towards the older end of that range. Some of the other trench events and the lake events might be a little bit younger, but they all overlap in their uncertainty. We pick up the 5,000 to 6,000-year event, 6 in Granite Canyon, 5 kind of everywhere else. There's the 3.4 event, which once again was this really high confidence event that we see from the cores and from the mapping. And then we have the 2.1 event, which is a little bit lower confidence than the 3.4, but I would still call this relatively high confidence because we see this event in multiple places. It fits the synchronicity criterion. And so, in conclusion, right on time. We saw about 24 individual turbidite and MTD events in this core section. Greater than 5 of those groups of MTDs were instantaneous intervals that we've identified as high confidence seismic events. Within those events, there may be some fore and aftershocks that cause both MTDs and turbidites, particularly for the 12 and 8,000-year events, which we think are the big show here so far that we've seen in Jackson Lake. We think there's 2 new events we've recognized at 3.4 and 2.1. And I say this, I would also like to caution you by saying that I'm a huge believer in peer review, and we are doing that now. That process has started, but this is not a peer-reviewed, published age for any of these things. So I'm putting that caveat out there for all the YouTube trolls. One of the things I think will be interesting if all this stuff stands up is that we're looking at the persistence of a 2 kiloyear recurrence interval roughly for the Teton fault. That's good and it's bad. It's good in the sense that it means that maybe we're not waiting on this like end of the world 5,000 year mega earthquake. It's bad because it's been 2,100 years since we saw the last one in this record. So I'll let everyone here, we got a lot of smart people in this room. We'll let everybody kind of do their own math. I don't want to come to any conclusions here. But we have to think about the implications for this next major seismic event. The other thing that we've been able to think about with this core, because it's so long and so high fidelity and so high resolution, we've started thinking about what other earthquakes it might be recording, what other systems could be feeding this. So this is this is work done by our colleagues at the USGS Hazard Center in Golden and some folks in Virginia. They've done this incredible study looking at Henry's Lake in Idaho and finding these young earthquake events like the Hebgen Lake earthquake. This is the Hebgen Lake earthquake in our core, and we're able to almost date this perfectly using radiochemistry, which is fallout chemistry that peaks in 1963 when the treaties were signed to stop, bombing everything above ground. So we can date this very accurately back to 59, but that's the Hebgen Lake earthquake in this record. This is the kind of thing we would have skipped right over in our core. We have a new student, Abby Portwood, that's working on this. And Abby is actually going back into this 100 feet of core now and looking for all these events so that we can understand the sensitivity of these cores to these sorts of things and the history they can tell us about the greater area around the Tetons. All right, so I'm going to end it with this really ridiculous photo. So we shot seismic in the northern Tetons over one of these scarps, and then we decided, like a bunch of fools, to stand on it like we just slayed an elephant and take a photo. So this is my group in the field, yeah, I'll take any questions that you have.
Knowing real estate broker?
I always, from the very beginning of this project, I hated, the science all makes sense to me. A lot of the bits outside of it haven't always. And I get the challenges that come with these sorts of things. And it's one of the reasons I put the caveat in about the peer review. I think it's important for us to get the community to agree with us about these things. I have shown a lot of this data to the folks at the Hazard Center, at USGS, and to other people. And we haven't gotten any major pushback yet, but it's not the answer. Like I said in the beginning, these things they're underwater events that may or may not be seismically derived, right? So that's the challenge. Yeah, sure.
How big are the seismic events that you are recording? What's your guess on the size?
So the question for Zoom was, how big are the seismic events we're recording? That's an even bigger challenge because the magnitude of the event is related directly to the amount of slip and usually the rupture length, how long this thing breaks. Based on our, looking at our data in comparison to other data where we see the same earthquake events in those ruptures, I would say that 8K event is probably one of these magnitude 7 or 8 earthquakes that, that people have sort of hypothesized for this area. Some of these younger events might be a little bit smaller, but it depends on how much rupture you have. And to know the length of the rupture and the amount of slip, you kind of have to be able to directly observe it. This is one of the pieces, though, for us that our new student is working on is understanding for modern quakes like Hebgen Lake, we have good shake maps. We know how much energy is released from the quake. We know how far it travels. And so making an equivalency between the size of the deposit that we get in the core and the shaking that we get, we think is really important. Now, there's another caveat that I didn't mention, and that's that the sediment to produce these events has to be available. So one of the reasons we might not see the 5,000-year event that we speculated is that not that it was small, but that the 8,000-year event shook down so much stuff that there wasn't anything available when the 5,000-year event happened. There wasn't as much stuff available, and it might be the reason that we miss it so many times.
So those 7 or 8 magnitude quakes, like the 8,000, How much slip happened on the fault at that time from the
Rich,
trenches?
2 to 2.5 meters. That's a big slip event. That's a lot. Yep. Oh, sorry. Yeah, sorry.
There any evidence of fires at those cores?
Definitely. Tons. Oh, sorry. The question for Zoom was, are there any evidence of fires in the cores? Yes. And there's a study ongoing for those now already. I mean, I'm sort of hoping that a lot of people that are outside our discipline will jump on these cores for other things. But there is a fire study that's been started. There's some big mega fires in there, some fires that look really scary in the core by the size, by how thick they are. And yeah, hopefully it's going to give us some insight into the fire history over the long term here. Yes, sir.
Well, I hate to admit that I'm a petroleum engineer and not a geologist,
That's okay.
but when you take this core, you went down 100 feet. What did you hydraulically push the pipe down 100 feet and then go in and remove each core, or how did you do that?
So the question was, how did we actually get the pipe into the mud to collect the sediment? It turns out most of this mud is so water saturated that just by setting the weight of the pipe with the 80 kilo weight on top of it and lowering it, it will go through this mud for the first, say, 10 to 20 meters. By the end, we were hammering it. So when the pipe goes down, yeah, if we want to say we want to go 60 feet under the lake floor, we'll put 60 feet of pipe on, and the bottom pipe will have a closed barrel, a piston at the end of it, and it will stay closed. It's shaped like a bullet, and it will just penetrate the mud while we hammer it down. When we get right above where we want to collect, we pull a cable and it fires that piston up the barrel and opens the barrel up. We push it down another 1.5 meters. Something closes the barrel, like a core catcher, and then we pull it to the surface. So we were doing it 1.5 meter drive. So we had 400 feet of water to descend, and then whatever depth we were going below the lake floor every time. So in the first few days, we'd get 4 drives a day. We'd make 6 meters. By the end, we were getting 1. And the weather was coming in, and we couldn't have our downhole assembly in the hole hanging from our rig when, I mean, you've seen the storms on Jackson Lake, right, with the waves. So we'd have to pull all that stuff up, and we'd have to get our crew off that was the most exciting part, was getting our crew off the platform while the platform's just getting tossed in these waves without smashing the platform or the boat. And so it was a learning experience.
How consolidated for your core?
The question was, how consolidated were the cores? At the top, if you took the plug out of the top of the core and turned it over, you dump it out. At the bottom, they were like hard clay. They were still soft, but you would have to poke at them. They weren't that easy. Yes, question. That's okay. No.
Just banging down, it sounds like the stuff is pretty soft. How much deformation are you getting just from your pounding that might be affecting the data?
Yeah, the question was, how much deformation do we get when we pound this thing in? And the answer is it's actually not nearly as much as you get with other coring techniques. Like we have like a lot of people take cores by doing what we call vibracore, vibrational coring. We can also use a rotary core tool, like something that spins the cores, and that's what they use a lot in industry. I didn't have the heart to ask Simeon to bring a drilling rig here. So, but this tool, you can actually see a little bit of flexure on the side, but this tool actually slides through this stuff pretty good. And some of our barrels, it was hard to tell even on the margins of the core that there was deformation in it. So they matched up really well with the seismic too in depth. So we don't think we compacted them too much. I mean, they didn't really get compacted that way, but yes, sir.
Would it matter what time of the year the events happen? Because if it was like in the spring when all the water's running off and there were slides way up high and all that sediment would also be. So is there a way to tell what time of year the events happen?
So the question is, was there a way to tell what time of year the event happened, because it could change the sediment that's delivered to the lake, right? And that's true. It depends on the fidelity, it depends on how well we're able to work out the layering in the core. Sometimes we can see the change in seasons in some of these cores. The challenge is that when these deposits come down slope, a lot of times they do a lot of scouring and a lot of digging. And so that's why when we dated them, actually what we're dating is the top of it, the new sediment that's coming on top of it. It's tough though. It would be tough to know the seasons, but I agree with you. I mean, like I said, after seeing some of these Helene deposits, it changed my mind about the scale of what can happen with landslides and fluvial stuff, even in a major rain event.
Two quick ones. Well, one quick. Was Jackson Lake covered by water this entire time that we're talking about?
The question was Jackson Lake covered by water this entire time? This depot center, we think so. Yes.
And my other question is, can you describe how science funding, government science funding being jeopardized is going to affect your work going forward?
Yeah, that's the question was, can I describe the challenges going forward with the way that science funding is being treated at the federal level? And that's a really simple answer. It's an absolute end to science like this. There is no commercial or other organization, for-profit organization, that will ever be interested in doing this kind of science for us. This is, it's deeply, it's deeply difficult for me to even talk about it because there's nothing that's going to be great about getting rid of these kind of things. And I think perhaps more importantly, forget the earthquakes. You know, I don't even have room on my slide for the number of people that have been trained. All those students you saw there, they're at engineering places doing like bridge evaluations for earthquakes. They're finding minerals in Reno, Nevada. They're working for state surveys. They're at the USGS. Like all the scientists that are doing all the important work in the country are trained on projects like this that are funded by the federal government. So
Sorry.
that's fine. I think it's important. I think that people need to be faced with the realization that all of these things have consequences and they're big.
Scientific monitoring and Jackson or this community, being on the fault line, or you have access to, or?
Yeah, you can see them all. So there's seismic instruments that are constantly recording. Yep. And they're all publicly available. We can see them. There's actually, because of Yellowstone, there's an incredible seismic network here. So we can see all of these things, and man, they're just really quiet, like uncomfortably quiet, mostly. So, yes.
Public safety implications for residents in the valley in the event that it went into 2005.
Okay, the question was, what are the public safety implications? And yeah, you want to answer that question? Sure. Can people in Zoom hear you? Here, you know, stand close to me.
Dr. Doom.
So what's gonna happen is very likely if we get that sort of.
The question was, what are the implications for the public safety in the event of one of these major earthquakes?
And what we think is going to happen, well, they're actually mapped floodplains for the Snake River. And as you know, there are levees by the bridge, and what's gonna happen is, first of all, if it's anywhere near Jackson Lake, it's possible that Jackson Lake is going to, and the sediment below Jackson Lake is going to start creating this seiche effect. And it's probably going to rupture the earthen part of Jackson Lake Dam, which is to the west of this, where you drive over it. And that's it, depending on how much water is in the lake, will flood the Snake River Valley. And so Jackson will be high and dry, Teton Village will be high and dry, Wilson will be underwater. And possibly as much as 8 feet of water. Now there'll be several hours of warning for that, but if you do live, I mean, I've got the map of the flood, potential flood area for the Snake River. So if you live in that area, you should have flood insurance. Just saying. I don't know about how much shaking, but certainly there will be shaking, and there will probably be landslides and or avalanches if it's the winter.
I would say, people ask me a lot of times when I give these talks of whether or not I want to see it. And it's kind of like, if it's going to happen anyway, then I'd love for it, not love for it, but if it happened in my lifetime, it would, because I've spent so much of my life working on this place, it would be great to actually see it if it's going to happen anyway. But every time I'm in these mountains and everything's loose around you and there's loose blocks everywhere, I'm like, please don't let it be today. So no, I think it's very serious though. I think it should be taken very seriously. It's one of the reasons I hate giving these talks in a way, because it's, you know, there's not always great news that comes out of some of these things, but it's better to know, right? And to be prepared.
If you look at a landslide map of Jackson Hole, it's almost completely covered with landslides. Because of the topography, it's so steep, except for in the flattest parts of the middle of the valley. Everything else is just covered in landslides.
But Slide Lake was not in the
No, that's true. So this is the 100th anniversary this year of Slide Lake, the
Like Grovon.
slide, and that was
Rain.
because of rain. In fact, that's a
I
great
learned that from
question, Jim.
Cynthia Blankenship.
Yeah, most of the landslides in the area, or a lot of them are not caused by earthquakes. They're caused by the steepness of the topography, and then in the case of the Grovant slide, that was combined with the dip of the sediment, the dip of the rocks that were dipping into the Grovant River Valley. And then there was a layer of clay basically that got hydrated, and that created the slip surface. And so all the material on top of that slippery clay layer fell into the valley basically.
It's worth saying that we have the data now to tell like where the landslide deposits are and where they've been in the past, and they happen in the same places. So one of the things that we saw coming out of Helene that was so hard to swallow and so devastating was the ending of 2011 of North Carolina's landslide hazards program. And a lot of people that died in that event in a landslide or in a debris flow lived on a landslide or debris flow deposit. And as soon as we drove into the valley, we could tell by the slope where the deposit was. It was mortifying. They're perfect slopes for building these things. It's worth having a look. So we have the LiDAR data now to do that. It's worth having a look. Question, yes.
I was just gonna, one thing about the lower Slide Lake is that there was a earthquake detected in Moraine the night before the landslide.
Oh,
And so
cool.
it's debated whether an earthquake was a trigger for that one or not. And then I did have a question about, can you tell the difference? So if you can pick out the Thigpen Lake earthquake, is there a signature between earthquakes that happen farther away versus ones that make you think that it was on the Teton fault? Because I could see you seeing shaking both from that fault, but also just it being a seismically active area.
Right. So the question for Zoom was, can you tell the difference between far field earthquakes that happen far away versus ones that happen on the Teton fault in the core? Admittedly, we got the Thigpen Lake earthquake was targeted because of the really, really tight geochronology that my colleague Kevin Yeager and his lab were able to do on that quake. And actually, we have short cores from all over the lake where Sam Whitehead, who's one of the graduate students working on this project with Kevin, is looking for Thigpen Lake in the uppermost parts of the lake around the area. It's one of the things we're working on to try to discern. Right now, I would say that it would be tough, but they are smaller. They should be smaller if they're further away and there's less shaking. It should be a smaller event. And this is one of the things that Abby and working with Sam are going to try to calibrate. So,
Got a couple of Zoom questions.
okay. So let's see. It says, can he replay the video without
No.
Oh, okay. Let's see. You're gonna make me dance or something. With the supersaturated soil. Okay, the question is, with supersaturated soil and there's a quake, is there any evidence of floods or anyone working on that? And I would say that we're going to be the people working on that. And it's only because we've been doing my group, along with a bunch of folks at the Kentucky Geological Survey and a bunch of people as part of a bigger initiative in our department from NSF called EPSCOR that's focused on flooding and hazards in Kentucky and in the Southern Appalachians. We've been getting really focused on the evidence for paleo floods. And so if there's paleo flood record that would contribute to these events, then we're hoping to be able to find it. Now I can say that not definitively, but I can say that a lot of these events are so big that we highly suspect they have, it's nothing to do with flooding, but flooding could be a root cause of a bunch of the smaller events we see in the core, and they need to be worked out. They need to be separated. In fact, we're laying down a brand new paleo flood event right now in Kentucky, the day before I left. So it's getting quite challenging there.
What's the definition of a paleo flood?
Just an old flood. We're looking for old floods that aren't in the historic record. Most of the ways we build bridges and dams and all those things these days are based on the historic record. Where have we measured these events? But with climate change, what we're seeing is that we're getting events that are way over the things we built our dams for, the things we built our bridges for. Jackson Lake Dam was built in 1980. What do you think our forecasts were? 1910. It was repaired in 1980. And all of those things are challenges. Most of the dams that almost failed during Helene were built before 1940. We have a lot of challenges ahead of us. But yes, the floods piece is really important. One more question. So it says, do you see any evidence of movement on the Teton fault that has altered the shape and or size of Jackson Lake? So Jackson Lake is a weird one because its southern shores are basically the terminal moraine of the Pinedale ice cap that came down out of Yellowstone. And this was all mapped out by Ken Pierce and his colleagues a long time ago. And I should mention saying Ken's name. Ken's no longer with us, unfortunately. He was an absolute legend around here. And he found archaeological evidence of this 2,000-year-old quake. And I should have added that in here. And I forgot to do that. So I want to say that now. Ken found this, and it's always been a little bit discontinuous. So I'm excited to share these results with his daughter and tell her about the fire record. So Ken Pierce's daughter runs the Earth, Wind, and Fire Laboratory in Boise. So, but I don't know. I think that the hole that's there, a lot of people think it's carved by glaciers. I think it's because it's where the most displacement on the Teton fault is. The glaciers might also play a role, but I don't think it's an accident that the deepest hole in the valley is right where we think the most displacement is on the fault. So maybe we just got lucky with this dirt hole with all the mud sticks, So my lakes colleagues have asked me to stop calling them mud sticks. So it's right there in Jackson Lake, right in the middle, right up against, you're right in front of Eagles Rest Peak. So you're just north of Moran Bay. Between Elk Island or Elk Island? I'm thinking of Utah. Elk Island and Eagles Rest is where that hole is. 425 feet is where we were deep.
That's the depth of the lake.
Yeah.
Right?
Oh, the hole, so the question for Zoom was how deep is the hole? We can see 90 meters of lake sediment in that hole, and it's sitting on top of glacial moraine, which is sitting on top of Cretaceous and Paleozoic rocks. I don't know. It depends on the geometry of the fault. I think the hole's got to be, 3-4 kilometers minimum, the total hole. Depends on how fast the fault dips down to the detachment. I was afraid so the question was, what is the rate of deposition? And I wish that my lakes colleagues were here, but it would be, we're looking at 12,000 years and 100 feet of core, 31 meters of core. So you're looking at God, now my brain's not going to be able to do basic math anymore, but somebody got a calculator? I think I figured out it was like 1.5 meters per 1,000 years roughly, but the sediment rates in the glacial are almost twice as much. Once we come out of the glacial, they slow down, which is not surprising. Glaciers produce a lot of sediment. Any other questions? No? Okay. Well, thank you all for coming. I really appreciate it.